Hi, welcome everyone. So AOCS has organized this roundtable discussion on green chemistry to supplement an article in the October issue of Inform magazine. And that article was titled New Developments in Vegetable Oil Materials Science. And it discussed how scientists are carving out niches for polymers made sustainably from seed oils. So our guests today are Neil Burns, who is CEO of P2 Science, and Karthish Manthiram, who is an assistant professor at MIT. And they were both sources for that article, in which Neil described how his company has developed a new way to perform ozonolysis that is being used by ADM and others to create ingredients for commercial products in industries like cosmetics, polymers, and surfactants. And Karthish explained his research on forming epoxides from olefins using electrolysis and the potential for applying that process to vegetable oils. If you haven't had the opportunity, I recommend that you read the article in the October issue. But I've invited both gentlemen here today to continue the conversation because I wanted to talk about ozonolysis and electrolysis as future manufacturing processes beyond seed oils. We seem to have approached a tipping point. Green chemistry and green engineering have gone from these fringe ideas to acquiring millions from investors. So Neil and Karthish have insider perspectives since they both work in the field of renewable manufacturing. And I welcome you to our conversation today. And I want to start by addressing the specifics of each of their expertise before we open up the conversation more broadly to what to expect in the future of green chemistry. So first, thank you both so much for making the time to be online with me today. Neil, I want to start with you. So P2 Science is a renewable specialty chemical company. And one of your co-founders is Paul Anastas, who is currently the head of green chemistry the head of Green Chemistry, Green Engineering, Center of Green Chemistry and Green Engineering at Yale University, but he's also known as the father of green chemistry. So with those roots, there must have been other commercial manufacturing options. And why did P2 Science choose to start with ozonolysis?
Yeah, great question. And it's a long story, which I'll attempt to condense into a bite-sized piece. Ozonolysis itself has been around for a while as a chemical process. It's been used in research labs for many decades. The common complaint about ozonolysis has been that it's very useful on a very small scale to synthesize chemicals. It's an oxidation chemistry. But then scaling up from the lab scale onto a commercial scale has been extraordinarily difficult. The reaction itself is quite exothermic. It is quite hard to control, notoriously hard to control on a commercial scale. And there have been traditionally with commercial scale ozonolysis a lot of safety concerns because of that. And so we recognized an opportunity here if we could make, as we call it, ozonolysis user-friendly on a commercial scale. It could open up a lot of opportunities to make products commercially that haven't been easily accessible before. So it struck us as something that was ripe for development if we could apply some innovation in process chemistry to make this process scalable, easily controllable, and safe. On top of all that, and maybe this isn't as widely recognized, ozonolysis, in addition to having been around as a chemical process for decades, it's been around in nature for millions of years. The process whereby ozone interacts with unsaturated carbon chains in vegetable oils, let's say, or in natural terpenes, which are present in forests and plant material. That interaction has been around for millions of years on this planet, and the sort of the hazy fog that you'll see above a rainforest, for example. A lot of what's there is the product of ozone in the atmosphere interacting with terpenes that are arising from the forest. And so that's a very natural, obviously very natural process, and we're taking that and doing it on an industrial scale. So the opportunity to do something industrially that's not only been around for a few decades, but it's also been around for millions of years, but has never been brought to a commercial scale before, was a super cool challenge for us, and so that's really what got us down this path.
Great. Karthish, your lab is developing nanocatalysts that use components from air, like nitrogen and carbon dioxide and water, in electrochemical reactions. So what types of compounds is your group aiming to synthesize with the electrochemical process?
Yeah, so as you mentioned, Rebecca, we're starting with these very basic building blocks, chemicals, or feedstocks like CO2, nitrogen, and water. CO2 is our source of carbon atoms. Dinitrogen gas gives us the nitrogen atoms that we need, and water gives us our oxygens and hydrogens. And then we work to facilitate this molecular level dance among these constituents to break their existing chemical bonds and then make the chemical bonds that we want in desired products. So at least one way that we motivate this is by looking at the carbon footprint of chemical manufacturing and seeing where that is. And the chemical that has the largest CO2 footprint of anything that we make today is ammonia. And so ammonia stands out as a chemical that needs to be decarbonized. And then from there are several other chemicals in the top 5 list, things like ethylene, ethylene oxide, BTX, et cetera. So these are some of the other major targets that our group is pursuing now. And so one can see how if we decarbonize the production of things like ammonia, ethylene, and ethylene oxide, the decarbonization of those is then inherited by all the downstream processes that make use of those feedstocks. So there's a way in which if you just start to decarbonize a handful of chemicals, you actually have widespread impact throughout the chemical industry.
I also wanted to ask you, there's been a lot of news reports about electrolysis in the past year, and they're often accompanied by the headline that says that you can make protein out of thin air. Can you familiarize everyone with how the electrolysis is being used in manufacturing and talk about the validity of that out of thin air claim?
Yeah, I think this is sort of in at least in some cases marketing gone too far. The notion that things come out of thin air is somewhat it's making use of the fact that a lot of the input feedstocks are gases. It's also water, so clearly water doesn't really even though there's moisture in the air, it doesn't really to me satisfy what is necessary in chemical synthesis. So if a device were to take just renewable electricity and just air, it's hard to make an argument that there would be enough CO2 present in the air at 400 ppm or moisture to do anything meaningful. That device would be transport limited very quickly. So this is a case where I think the marketing really needs to be dialed back a bit to reflect the reality of using concentrated CO2 feedstock, so effluents, coal-fired power plants, or other processes that like cement production, which make higher purity CO2 streams. And the fact that we really should use condensed phase water rather than moisture in the air. It makes for a very interesting concept, but it's not something that I think has as much grounding in the near-term commercial prospects.
Neil, can you talk about the products that P2 Science has launched so far? Follow up on that, have you focused on replacing existing petrochemically sourced products, or are you exploring new compounds? And then how do your products compete as far as price, performance, production scale with existing specialty chemicals?
Yeah, so we've focused in initially on some lower volume markets for our technology. And the first market we took a close look at is flavors and fragrances. Volumes are quite low, prices tend to be quite high, and we've deployed our ozonolysis capability to oxidize unsaturated fatty acids from things like soybean oil, sunflower oil, etc., ultimately producing aldehydes for fragrances. And so we have a commercial product we launched earlier this year, which is available on our website. You can buy it at the web store. It's bio-nonenal, so it's a linear C9 aldehyde produced from a vegetable oil source. Traditionally, this particular aldehyde has been available primarily from petrochemical sources. If you wanted something from a vegetable type of source, you'd have to pay several $100s per kilo for an extract, a fruit extract, a citrus rind extract, which, in addition to being very expensive, often came with potential allergen concerns. So what we're producing is a very pure, allergen-free, naturally derived linear aldehyde for use in flavors and fragrances. It's priced extremely competitively versus the citrus extract option, a fraction of the price, actually. And it's a little more expensive than the petrochemical option. And we found a huge interest from folks that want something natural and bio-derived, don't want to take the risk of dealing with potential allergens, and don't want to pay several $100s a kilo. So, you know, that was part of this, I guess, a deliberate strategy to enter the market in areas where small volumes would be quite meaningful, and there's opportunity for reasonable pricing. You know, you're not battling it out with benzene pricing or ethylene pricing in high volume commodities. Some of the areas along similar lines, similar markets that we've targeted are cosmetics ingredients, where again volumes don't have to be huge. There's opportunity for premium pricing, and at the consumer end of that market, there's considerable interest in having ingredients that have a good story, that are naturally derived where possible, that are benign not only to the skin and the hair or wherever the application area is on the person, but also benign to the environment. So we found a lot of opportunity there. And again, you'll see on our website a bunch of products that we've launched just within the last year that are going into cosmetics and personal care, for skincare applications, use in makeup, color cosmetics, hair care, shampoos, conditioners, etc. So we've got a fairly ambitious program actually, where we've been for the past 6 months, 7 months, I should say, launching a product per month, and we intend to continue that pace until the end of next year at least, because you know the pipeline is quite full. So yeah, that's where we are in a nutshell.
So you've been successful with finding customers who are interested in a sustainably sourced product.
Yeah, I mean, you know, it comes back from consumers. You know, the consumer product business is in the business of meeting needs of consumers, and certainly in Western Europe, North America, Japan, I would say the advanced economies, there's been an increased interest on the part of the consumer in things that are natural or bio-derived, and as I said, you know, an increased interest in just what the effects of these ingredients are. And so I guess coming originally out of Western Europe, you know, this is very much a mainstream consumer segment in all those advanced markets. It's not to say that everybody wants everything natural, but certain folks do, and it's no longer a sort of a minority segment. You know, if you remember like 20 years ago or so, when companies like Seventh Generation or Aveda were coming into the foreground, you know, they were very much a quirky kind of brand appealing to a minority segment. But today, you know, it's very much a mainstream concept, and so that's basically what we're reacting to is just meeting that consumer interest, that consumer need is, you know, expressed by what people buy and what they ask about.
Yeah, you bring up a really good point, and I'd like to now kind of address the conversation to both of you at the same time and shift into, now that we understand what you guys are doing individually, shift into more wider view of green chemistry and green manufacturing in general. So it seems that originally, when the motivation was coming from the industry, the focus was on replacing petrochemicals' primary products, fuel and polymers. But now that it's more consumer driven, we've shifted into plant alternatives, and green manufacturing is actually scaled back and isn't aiming for such a big leap in such massive petrochemical products. So do you think that scaling back has actually given green chemistry an opportunity to take a leap forward for a more renewable future? Karthish, do you want to address that?
Sure, yeah. So I think there's this way in which what captures like the minds of researchers are often these targets that have very large impacts, right? So when one looks, for instance, at decarbonization broadly, probably the first thing that we think about are things like fuels, that there's an enormous CO2 footprint behind the energy that's needed to power our economy. And so from that perspective, it's a very natural sort of starting point to want to create technologies that address those things. But what we see time and time again is that technologies that are competing for commodities are extremely cost sensitive, and the consumer tends not to express as strong of a preference in those markets or the downstream products of those markets in many cases. But when something is actually direct to consumer and those things are marketed to them and they see directly the impacts of it, they tend to care more. Those tend to be things then that are further downstream, right? And so it's for that reason that I think, even though our research is focused first here in our own lab on commodity decarbonization, a lot of the first commercial impacts are going to be on things that are smaller scale, fine chemicals, and things of that sort. And then hopefully these technologies will mature to a point that they can move up to the commodities over time. But this sort of thing we've seen in many different industries. So I think whether it's for instance, with solar panels. Solar panels were initially sort of a curiosity for space, and were only really usable in a very small set of circumstances. And one could very easily make the technical argument that these would not be viable. But 50 years later, we see that these are competing in a wide range of markets, and I think everyone can kind of see where that trend is headed. Same is true with lithium-ion batteries. That lithium batteries were developed. The earliest manifestations of these were developed at Exxon in the 70s, and there were internal meetings at Exxon with discussions on whether this is something that more money should be put behind or just kind of left to the broader community. And the decision at that time was that this was something that did not have a large enough market to be immediately useful. And that in turn meant that, of course, this technology found its grounding with consumer electronics instead of things like electric vehicles and things of that sort. And that's the right place to start, right? There's a much larger premium that you can pay for a battery that cost $30 and instead pay, on a battery basis, a battery that costs $30, you can instead pay $60 for it. But at the scale of an electric vehicle, you're not going to want to pay that. You don't want to take a car that costs $30,000 and pay 60 or 90 instead for the broader market, right? Of course, elite consumers can do something different. So there are a whole bunch of cases where we see time and time again that things start niche applications and then grow out, whether it's solar panels, lithium-ion batteries, and the same is true for bio-based processing and probably for electrochemical processing as well. In many ways, if that same paradigm will hold true. There are always exceptions to this, but that's a very general way, I think, of looking at this problem.
Neil, do you have thoughts?
Yeah, I think your question was phrased very nicely. Has the industry in essence gone forward by taking a step back? And I think that's absolutely right. When I think about some of the companies that I thought were very strong technologically in the mid-2000s in this area, two in particular come to mind, which I really fell in love with technology-wise, and those were Solazyme and Elevance. Solazyme's algae fermentation technology to convert sugars to oils was really phenomenal. Elevance had a metathesis-based technology based around processing vegetable oils into new chemicals, new oligomers in many cases. Both of those companies are not around today. They had great technology. Solazyme in particular started out with an ambition to replace diesel fuel, right, with a vegetable option. A huge prize, but very, very challenging. And they took a few steps back as they got into that challenge, but ultimately the company itself just wasn't able to to make money in its chosen markets based on the cost levels that were necessary in those markets. And so, you know, having been through that, I think a lot of followers of those guys, us included, P2 included, learned the lesson not to throw everything at the biggest prize out there, but to take smaller steps towards growth and viability. And actually, you'll see a number of companies being very interested in the markets that we're currently in, like flavors and fragrances and cosmetics, where, as I said, those volumes are not as huge and the cost targets are more diversified. Not everything has to be less than $2 a kilo. Some things have to be less than $200 a kilo, and some things have to be less than 20. And you know, there's just a huge diversity and variety. And as Karthish says, that when consumer preferences come in more into play, it's less of a clear-cut economic algorithm that you just apply and the answer pops out. You know, it's not like that, and so there's more opportunity again to make progress in those areas.
Yeah, I totally agree with what you're saying. It seems like fragrances, cosmetics, those types of ingredients, and then proteins are really what are pushing the market right now. I mean, everybody's using more green technology for those ingredients. All right, so let's talk about the idea of a cyclical economy, where green chemistry is used to power green engineering is used to power green manufacturing, just enough so that specialty chemicals and food ingredients satisfy a limited market. It seems possible, given the reduced cost of solar power and the establishment of manufacturing processes like fermentation and ozonolysis and electrolysis. But is it probable, given the economy of scale, since a company producing more can charge less? Neil, what do you think?
So you're asking me, sorry, the question is it probable that companies will be able to charge less, given that their cost position will come down with volume?
Right. I mean, the economy of scale. So if you have, if you're manufacturing just enough based on green engineering supplying your manufacturing plant, is that really economically viable? If you have a competitor that can truck in, you know, tons of whatever ingredient is needed at a significantly less price.
Okay, gotcha. All right, so there's actually two strands to your question. One is economies of scale. Yeah, economies of scale are a thing. I mean, it's like, I feel like it's almost like a fundamental law of physics, right? It's been around for so long, and it's
or
and it's one of the yeah, whatever. I mean, no, I like to think of it as a law of physics, because, you know, it's so baked into how things evolve. Yeah. And the chemical industry is no exception. And we see it in our operation. I mean, the plant we have in Connecticut today is about 500 metric tons per year capacity, and that implies a certain set of economics. We can deploy, and you know, part of our work with ADM, as we discussed in your article, part of that work is around deployment of basically the same technology at tens of thousands of tons, 20,000, 30,000 tons per year scale. Costs will come down dramatically because, you know, the staffing of those plants is not that different, honestly. The infrastructure is not significantly different. There's a lot of benefit to having scale, and that's a feature of process industries, process chemistry. The innovations, and that's really our technology at different throughputs.
You have the technology to meet that scale, that level of scale?
Sorry, say that again?
You have the technology to meet that scale?
Yeah. I mean, one of the features of our technology is it's very, very scalable. We're basically running the reaction in a process-intensified manner through a series of vertical tubes, and you basically number up the tubes to increase the capacity. And that's part of the innovation behind what we do. Is it's a very, very scalable, highly process intensified and modular type of production system. So it lends itself very well to taking advantage of economies of scale. So that's one thing. And, you know, finding the right outlets to be able to scale up, you know, like a series of stepping stones from fragrances to cosmetics to polymer intermediates for more larger volume applications like fabric and packaging and so forth. It is part of that accretion of scale. But the other strand of your question, I think, is maybe even more interesting and fundamental, is that, you know, we're not just competing on cost and therefore on scale as a driver of cost. Because a lot of what we're using our technology to make are unique products, are different products, are patented products. So we've got a whole line of patented cosmetics ingredients that no one else is able to make today. So, you know, can someone come along and operate at a larger scale and make our stuff? No, we own the composition of matter. And so I think it's important to put all your technical tools together, not just your process chemistry tools to get scale and find an alternative feedstock, but also look for opportunities to develop something genuinely new, as well as being green, you know, so that you have a further point of differentiation. You have the ability also to, you know, protect what you have via patenting. And that's, you know, that's a huge part of what we do also. Going head to head on something that's just the same, only green, it's not very interesting for us, honestly. And so, you know, that's not something we look to do.
I want to come back to that, but then I want to let Karthish address the question about the hope of green chemistry versus the reality of producing at massive scales.
Yeah, and I think what this really comes down to is, are there going to be new technologies that we develop that actually enable even more modular production than is possible today due to very different scaling laws? And so these driving forces of temperature and pressure that so much of the chemical industry is built around are driving forces that have scaling exponents that are relatively large. You know, to a first approximation, one can think of these, even though this is not quantitatively true, one can think of them as being processes that scale to the third power because they tend to be volumetric. I'm exaggerating a little bit because it's generally non-integer scaling when one looks at the full process, but these are essentially vessels in which you're
designed to produce enough to be shipped around the world, right? So it is a massive volume, right? Yeah.
Exactly. So these are paradigms in which you're putting up chemical plants at the scale of generally $1 to $3 billion a year for the large commodity type production, at least. Sorry, so $1 to $3 billion per plant, not year, but $1 to $3 billion per plant. And your goal is to you know, produce at a scale at which one actually realizes the cost benefits for a volumetrically driven process that requires temperature and pressure. So the question is, do other driving forces scale differently? And that's something that I think in laboratory research is being realized more and more, which is that electrochemical technologies are ones that scale with a smaller exponent, which means it is actually in some ways it can be advantageous to operate at smaller scales because you have this turnover point where you would rather make it close to where it's needed and save on distribution. Now, that is very product dependent, depending on how hard it is to distribute something, how much inventory cost, whether that is genuinely renewably powered, and hence you should make it close to where that renewable power is available. There are a whole bunch of things that go into that calculus, but there is this possibility that if technologies emerge that have smaller scaling exponents, that there could be a benefit to operating in a more modular fashion than we do even with processes that are termed as being modular otherwise today.
So you're saying that it's the production process itself that requires such a large scale and then shipment around the world to reap the cost of that production for the petrochemical industry. The pressure and the temperature costs are reaped by making so much of it. Is that what you're saying?
One way of looking at it. So if for instance, something like Haber-Bosch, which requires temperatures of 400 to 500 degrees centigrade for the actual ammonia synthesis step, along with pressures of 200 bar. So it turns out that those compressors are a large part of the driver for centralization. Compressors become cheaper per unit production as they become larger and larger and larger. And these are pretty ridiculous pressures as well. And so, in a relative sense, there are safety reasons as well for centralization. But compressors end up being the biggest economic driver of centralization. Now, what you give up then, and what you're compromising on, is the cost of distribution, right? If there was, a miniature modular Haber-Bosch plant, every 100 miles, distribution looked very different than it does today. But at present, we make it in a very centralized fashion and then push it out. Now, distribution is cheap in some countries, right? In the US, distribution is relatively cheap. So it's not as big a factor here. But in other parts of the world, especially in the developing world, distribution is still extremely expensive, to the point where, for instance, in sub-Saharan Africa, the distribution of fertilizers leads to an end price that's 2 to 3 times the international average. So these are situations where a distributed manufacturing paradigm could really change things. We've already seen that with solar power in sub-Saharan Africa. There are grids that are 80% solar driven, and which is remarkable, right, relative to most parts of the world. And this is because where there are failures of centralized governments to put up the infrastructure that's needed, you need technologies that smaller communities or individuals can adopt. And so that's certainly true for solar power. For chemical manufacturing, these will need to be community level or larger operations, but at least the incremental capital that's needed would hopefully be 10 times or 100 times smaller than this 1 to 3 billion type figure that's tossed around for Haber-Bosch.
That's really interesting. So let's go back to developing new products. I love the thought that, 100 years ago, nobody was sitting around thinking to themselves, it could really use a polyethylene plastic bag to carry my stuff in. So, we tend to develop the products from the technology and the compounds that we create. What do you see on the horizon for green chemistry, green manufacturing? What interests you from your vantage point in the industry as far as developing products or developing new molecules? I'll let Neil start.
Wow, I mean, that is a heck of a question. And it,
All right. I don't think
gosh,
small thoughts.
Yeah, you don't think small, and I appreciate that. I'm going to have to think here rather than give you a canned answer. I think what we look at.
What came to mind when you were talking about the patented products that you're currently creating? We don't have to go as big as the next polyethylene.
No, I know. I think it's a great question. I think it's a great question. I mean, when we think about the markets that we're in, and actually when I think about the markets that chemistry's in, ultimately you're kind of meeting the needs of human civilization, right, on this planet. And so, you think of that basic, your old Maslow's hierarchy of needs, right? I mean, you take care of the basics like food, right? As a lot of the chemical industry is supporting putting food on the table, and shelter, right? And the real basics, and clothing. I mean, the amount of chemical industry behind each of those layers of the pyramid is huge, and that's really, that's not going to change. Even getting to things like cosmetics and personal care and fashion. I mean, these are ultimately basic human functions for, attracting the opposite sex and all that. I mean, so these are still all all basic kind of human needs that the industry is meeting. And I read something, I think it was just yesterday, from the American Chemical Society that said 96% of US manufacturing is supported by chemistry. And I'm thinking, well, what is that other 4%? I couldn't figure out what it would be. It's a pretty powerful statement. So, I mean, ultimately, those are where our markets come from, and there's opportunity for green chemistry in all those markets. I have here in front of me. I'm not going to read them all, and I have printed them out because I used to have the book, but I think I lent it to someone. The 12 Principles of Green Chemistry. Okay, and this was published in Paul Anastas's book, which was published in 1998, so 22 years ago. And I think at the time it was considered a bit revolutionary. But when you look at some of these principles, I mean, most of them are common sense. The first one is prevent waste. Well, who doesn't want to prevent waste? I mean, you know, this is a the principles force you to think about these things explicitly. The second one is atom economy, which is kind of a chemistry thing, but it ultimately goes back to preventing waste, and so on and so forth down the list. You'll see there's nothing on here that's esoteric or weird or, you know, idiosyncratic or kind of nichey. These are all very, very common sense things. Real-time analysis for pollution prevention is number 11, for example. I mean, who wouldn't want to do that if you think about these things on a common sense level? So, I mean, I think, you know, your answer to the question, where do the markets come from? They come from, you know, the needs of life on this planet, which the chemical industry to date has done an incredible job of supporting. And the opportunity for green chemistry is just to make that even better by, you know, doing some of the existing things better and giving ourselves the opportunity, especially as you bring in a lot of these new feedstocks, whether it's vegetable oil or the air, as you said, bringing those into the picture and enabling you to do new and different things. So that's just the whole world, and just the whole of civilization is where the markets come from.
Well, I think my intention with that question was that green chemistry is competing now with a whole industry a whole market that the petrochemical industry has provided for us. So it's not just that we're trying to satisfy human needs, we're trying to satisfy, or we're trying to pull customers away from the petrochemical products that they've learned to love and use green chemistry products instead. And so that seems like a challenge. Karthish, what do you think? What do you see in future products where green chemistry can address those products?
Yeah, so I'll say something that might be a little bit kind of controversial, but at least there are things that you that one gives a consumer that that the consumer doesn't even realize, but through experiencing a product, feels that their life has actually become better, right? I think like the most classic case of the last 20 years is the notion of the iPhone, right? That no one or a smartphone, that no one really knew that they needed this thing that would, you know, give them direct wherever they go, tell them where the nearest coffee shop is, make it easier to do video calls and be more productive on the go. But since having it, I think most would agree that their lives have improved in some way, right? You know, now there are a whole bunch of issues that come with it as well, but there are a whole bunch of efficiencies that have been realized, and somehow we're saving time, we think, at least, or have better lives because we have these devices. The question that then arises in making the world more sustainable is, well, how does this make people's lives better? And I think sometimes it's a difficult argument because it's a collective argument that one often makes based on externalities, right? We're having to tell people, well, look, like global warming is an issue, right? Or if someone dumps waste, that is going to hurt the next generation, right? And one is having to make this argument that, you know, it's not necessarily your life that's going to be directly impacted, but all our lives together, right? And so, and this can be a hard argument to make at times because, you know, whether I go to the sink and I use a 7th generation product that's more sustainable, or I use a conventional hand soap, you know, the consumer may not, you know, really feel that as strongly as they do, that they feel they're acting and doing something good for the world, right? And that, I think, is sometimes what makes this difficult, right? Because you're trying to grab someone by the heart and tell them you have this greater purpose to do something good for the world. Now, there are ways of flipping that, right? You know, I think electric vehicles are a great example of how this has been done. That all the initial manifestations of electric vehicles were do something good for the world. Drive a Prius because you're going to do something good for the world, right? That was a big part of that argument. And it took instead electric vehicles becoming more fun to drive, and electric vehicles being a statement and cooler looking cars that allow you to do much more interesting things around this new age powertrain that are actually going to end up making electric vehicles successful. And one has to try to, and that's something that a human can say, well, this is better because I no longer have to go to a gas station. I bring it home and I charge it, and I have a more interesting driving experience, right? And that's good for them. And then so green chemistry has to ask more of these questions of itself, and people are figuring it out gradually, but we have to figure out how to make individuals feel that their lives are better because they're using these products.
Yeah. And one thing that comes to mind.
I'll add something else to that, Rebecca, you know, I've been in and out of chemical plants and chemical labs my entire career. So it's getting on for 40 years. And in the last 20 years, you would be quite surprised and amazed the number of labs. So I'm talking about where the basic genesis of new products is taking place that have these pinned on the wall, these 12 principles on the wall in the lab in big chemical companies that I'll name them: BASF, Evonik, Croda, Dow. You'd be surprised the number of labs that have these on the wall. These guys are just, you know, yeah, okay, designed for degradation. I'll keep that in mind, right? And it's sort of it's I don't know, it's weaving itself into the mainstream. It's becoming something that's not explicitly sort of talked about, like, oh, I'm going to make this project a green project. You know, it's probably something we're going to do anyway, you know.
Right.
And so it's a little more subtle than kind of a head-to-head between the old industry and the new industry. I don't think it's like that anymore.
Really? They're integrating, you think?
Yeah, definitely. I see that. I see that at a very basic level.
Well, the reason that I originally wanted to write the article that you all participated in the way that I did was because I look at building materials and how petrochemically derived building materials have really changed our lives. I mean, the durability and the you know, the function of those materials is difficult to match. That being said, I mean, we did develop an epoxide to make plywood that is comparable to an epoxy a resin that is that am I using the epoxide that's petrochemically derived. So a product like that, you know, when you're able to reach that kind of level of functionality, seems like, you know, we have we're taking positive steps, that there is a capability in the future to be able to match the function and the durability of those building materials. But there's a lot that has been developed in that industry. And so that's kind of how I started approaching this article. And it really made me think, like, wow, we have a long way to go if we, you know, if you really thought of it as like replacing everything, which, as you're saying, is not the way to think of it.
Yeah, I think that building materials are an especially interesting example because they're just so responsible for the quality of life and improvement in quality of life worldwide. And there are many that still have not received the benefits of things as basic as building materials, right? And so there's just absolutely no tolerance for increase in price, which is almost what any offering that's going to be greener for those is going to end up being more costly. And so, so this creates even more technical pressure to develop cheaper solutions, but creative policies that can help as well in recognizing the externalities of making sure those costs just don't get passed on to the poorest who still have not gotten the full benefit of all those advances.
Mm-hmm. All right, so here's my big final question. So in 100 years from now, do you think that these large chemical plants that we have all along the Gulf Coast will be dismantled, and then we'll have more of a town by town, you know, resource center that supplies everything that you need with using green chemistry and green energy?
Wow. I might tend to give you a controversial answer. I sincerely hope not. That would be a great shame. There's a lot of great assets. There's a lot of incredible technology there. To think that you could not repurpose plants if necessary, which we're already seeing in many cases. You know, there's a lot of European refineries refining, not a lot, a number of European refineries refining vegetable oils, right, rather than just petroleum. And you know, I think that's great. And so, yeah, I don't view it as, you know, King Kong versus Godzilla. Although I love that imagery, you know, I can't do it. I can't apply it here. Just can't get there. So no, I don't think that those things will be dismantled. Maybe repurposed in some form, but certainly I don't see a sort of the Clash of the Titans type of scenario here. Again, because of this, because I've seen this all over the labs, weaving its way into how things are done subtly, and in some cases not so subtly. You know, now, you know, if Karthish's work on the Haber-Bosch process is successful commercially, I mean, that's fantastic. You know, Haber-Bosch process transformed civilization, right? That was truly something amazing. And if you can revolutionize that and almost break the economies of scale associated with that would be a heck of a thing, and that would certainly restructure a huge part of the industry, no doubt about it. But the industry as a whole, I don't see it in quite those terms.
Mm.
I think when I look at this, my real hope is that we can achieve zero carbon petroleum processing, right? So that, in other words, if there's a carbon atom in petroleum and we need that carbon atom in a product, let's get that carbon atom from petroleum into that product with no externalities. And that's something that's still unrealized today, right? We invested a great amount of energy in steam cracking. We burn hydrocarbons to do that. That should be electrified or something of that sort, at least in the heating to be renewable. Now, of course, electrified heating is very expensive relative to hydrocarbons, so a great challenge to be solved, right? Or in the case of ethylene epoxidation, ethylene is epoxidized to ethylene oxide, but there is a significant over-oxidation product to CO2. So let's efficiently get petroleum into the products with mapping of those atoms, right? This is the atom economy concept that Neil mentioned, and avoid the externalities. And if we avoid the externalities, there's a bright future for petroleum. If there is not gusto and energy in achieving that atom economy, then the industry is going to face significant headwinds with the policies that are coming up in the near future.
Well said. Hear, hear.
Okay. Well, that is all the questions that I have. I would throw it out to our audience. If you have any questions, you can type those into your questions application there. One thing before I say goodbye, if nobody has any questions, we didn't really talk, Karthish, about some of the nanocatalysts that you're excited about. Is there anything there that you want to discuss? Sure,
yeah, I'm happy to mention a little bit about that. So there are several processes that our lab has worked on developing. There are at least two that I'll highlight that I think help to show the principles that we're setting forth. One is a process through which you can convert nitrogen and water into ammonia at ambient conditions. So with no heating and no pressurization, those are the conventional variables. So we hold the world record right now for being able to convert nitrogen and water to ammonia at the fastest rate shown to date. This is still a process that, despite achieving high rates and selectivities of around 50%, has an energy efficiency that's relatively low. But we have a roadmap by which we're going to work on improving that energy efficiency and clear research questions that we've articulated. We have a team of several in our group that's working on addressing that. We think we might be another 5 years or so from addressing many of those. But these are high-risk undertakings, right? There's some chance that we won't be successful, but we try nonetheless, knowing that if we are, then that would be something that could be relatively impactful. But this, in turn, would be a device that takes in water, breathes air, gets nitrogen from that, and actually makes ammonia. So that's a case where pulling something out of air with water actually makes sense. There aren't many chemicals for which that actually makes sense, though. And then the second example that I'll mention is making epoxides. Epoxides lead to very large carbon footprints. Ethylene oxide is the 5th largest CO2 footprint of any chemical that we make today. And so we need to find ways of making this very relatively simple collection of carbons and oxygens and hydrogens more effectively. So we've been learning to rip O atoms off of water and place those on an olefin to make it into the corresponding epoxide. So this is a reaction that looks non-intuitive, right? Olefin plus water goes to epoxide plus hydrogen. The conventional driving forces should not be able to do that reaction, right? Temperature and pressure. We think of olefins and water as just being inert to each other, right? But if you apply a suitable potential, those bonds rearrange, and we're the first to show a catalyst that can actually do that. That's very early stage research, and so we've shown for the first time that reaction can be done, but it's relatively inefficient. So there's a lot of work to be done in terms of making those processes work, but it really shows the early promise of this sort of processing paradigm.
Wow, that's great. Very cool stuff.
Very good.
Well,
Fantastic.
if we have no questions, then we'll just go ahead and wrap it up. It's been really fun talking to you all, and I really appreciate you participating in a roundtable with us, something new here at AOCS. And good luck in all of your research and consumer efforts.
Yeah, thanks, Rebecca.
Thanks very much, Rebecca. Appreciate it.
All right,
Thanks.
bye.